Good afternoon. Today we will be discussing the topic of magnetic field and magnetic circuit. The main points that are going to be discussed under this chapter are going to be magnetic field, magnetic flux, magnetomotive force, which is also called as M.M.F, reluctance and flux density. To begin with, let us see the definition of magnetic field. So, all of you would have been familiar with using a bar magnet in school. So, the space or region around the magnet where the magnetic flux exists is called the magnetic field. So, you can observe this is a bar magnet which has got a north pole and a south pole, and the region around the bar magnet where the magnetic flux exists is called as the magnetic field. These magnetic fields can be visualized as lines of flux that form closed paths. We know that any current carrying conductor So, we know that any current carrying conductor sets up a magnetic field around itself. Now, and if you place a magnetic compass in that, you can see that it is going to align itself in the magnetic field. Magnetic fields can be visualized as lines of flux that form closed paths. Using a compass, we can determine the direction of the flux lines at any point. So, if this is the bar magnet and a coil is wound on the bar magnet, and if a compass is placed in the vicinity of that, the compass aligns itself in a particular direction. Now, let us see the definition of magnetic flux. Magnetic flux, these are imaginary lines of force which exist in a magnetic field along which a unit north pole moves if it is free to move. So, this area around the magnet where the flux exists, the lines of force here are called as magnetic flux. So, these are imaginary lines of force which exist in a magnetic field along which a unit north pole moves if it is free to move. Magnetic flux is denoted as phi m or just as phi. The unit of magnetic flux is Webers. The magnetic flux through a given surface is proportional to the number of magnetic field lines that pass through the surface, and we can observe that the magnetic flux always emerges from the north pole and converge at the south pole. You can observe here that the magnetic lines of force emerges from the north pole and converges at the south pole. You can just follow the lines here which shows or depicts the magnetic flux. Now, the magnetic flux, they are also called as magnetic lines of force. Now, why is it called as magnetic lines of force? Let us consider a simple experiment. Take a sheet of paper and place a bar magnet on it. Sprinkle some iron filings near the bar magnet and lightly tap the piece of paper. You can observe that the iron filings starts aligning themselves or rearranging themselves in a particular pattern. And you can observe that the lines here shows that the iron filings have aligned themselves in a particular pattern. If you now place a compass in this region, that is the magnetic field around the bar magnet, we observe that the north pole of the compass tries to move away from the north pole of the bar magnet. So, if we are going to place a compass in this region, that is in the magnetic field around the bar magnet, the north pole of the compass tries to move away from the north pole of the bar magnet. This shows that a force exists in the region around the bar magnet. Now, this force or lines of force along which the compass moves is the magnetic lines of force, which is also called as flux. Flux is given by the equation phi is equal to B into A. Now, where phi represents the magnetic flux is the product of B and A, where B is the flux density and A is the area of cross section. Now, to understand the equation, we will have to understand the definition of flux density. Now, flux density is defined as the number of flux passing through each unit area of a magnetic field at right angles to it. So, it is defined as the number of flux passing through each unit area of a magnetic field at right angles to it. So, if there is a magnetic field at right angles to it, how it is going to pass, and the number of magnetic flux passing through a unit area gives the flux density. The SI unit of magnetic flux is Weber per meter squared, and it is represented by B. It is represented by B. So, now here you can understand magnetic flux is given by this equation B into A, where B is the flux density and A is the area of cross section of the field. So, the equation is B is equation for flux density is B equals phi by A, where phi is the flux in Webers, A is the area of the magnetic field in meter squared. Therefore, the unit of flux density, which is flux per unit area, is given as Weber per meter squared. Now, let us understand the next concept of magnetic circuit. Now, magnetic circuit is made up of one or more closed paths containing a magnetic flux. Just like you are familiar with an electrical circuit which has an EMF source and a resistor, likewise a magnetic flux can be made up of one or more closed paths containing a magnetic flux. The flux is usually generated by permanent magnets or electromagnets, and the path is confined to the magnetic core. So, you can observe here. Now, this is the path for the magnetic circuit. Here we have a coil of N turns which is wound on a magnetic material. A is the area of cross section, A is the area of cross section of the path, and this is the coil which is wound. So, whenever it is energized, that is a current is passed through the coil, magnetic flux is going to be set up, and the path where the flux is set up is here. This is the path. You can observe in the cross section here. So, this is the coil, and here you can observe these dotted lines is nothing but the flux, and this is a core of iron, and here is an air gap. So, now we can understand what is this magnetic circuit. It is defined as the path in which magnetic flux exists or intends to exist whenever a magnetomotive force is applied to it. Whenever a magnetomotive force is applied to it. That means, it is a path in which magnetic flux exists or intends to exist. That is, as you can observe here, this path, along this path the magnetic flux tends to exist. Whenever a magnetomotive force is applied to it. Okay. We will move to the next definition of magnetic field strength, or it is also called as magnetic field intensity or magnetizing force. So, we know that the space around the magnet, there is a strength or a field existing there which has a force. Now, that magnetic field strength, how do we define that? Is also called as magnetic field intensity or the magnetizing force. The magnetic field strength at any point in a magnetic field, you can observe the field here, okay, in a magnetic field, is the force experienced by a unit north pole. See, you can observe here, this is a unit north pole, by a unit north pole placed at that point. So, let us come again. Magnetic field strength at any point in a magnetic field is the force experienced by a unit north pole placed at that point. Now, this force varies from point to point. The force nearer to the poles is different. The force somewhere here is going to be different, or somewhere here it is going to be different. That means to say, it varies from point to point. The magnetic field strength varies from point to point. You might have done a simple experiment using a simple bar magnet, where when you hold the iron filings near the bar magnet, you observe that most of the filings attach themselves nearer to the poles than along the length of the body of the bar magnet. Okay. That is because there is more magnetizing force near the poles compared to the length of the body of the bar magnet. So, here the magnetic strength at any point in a magnetic field is the force experienced by a unit north pole placed at that point. The SI unit is newtons per Weber. It is denoted as H, and the equation for it is given by M.M.F by L AT per meter. AT means ampere turns per meter. The unit of M.M.F, that is the magnetomotive force, is ampere turns, and the unit of length is in meters. Thereby, H, which represents the magnetic field intensity or force, is given by AT per m, that is ampere turns per meter. So, we have been talking about this M.M.F, that is the magnetomotive force. Now, let us actually define what is this magnetomotive force. Now, it is the force which creates or tends to create magnetic flux in a magnetic circuit. So, we have a magnetic circuit and it has to create a magnetic flux. So, you can observe here, suppose there is a magnetic material on which a coil is wound, and if the coil is energized, that is you pass electric current through it, then it sets up a magnetic field around itself, and these lines are nothing but the magnetic flux. So, magnetomotive force is a motivating force for the flux to be set up. So, it is the force which creates or tends to create magnetic flux in a magnetic circuit. It is very much similar to the EMF in an electrical circuit. It is given as the product of the number of turns on the coil and the current flowing through the coil. So, you can observe here, we can vary the number of turns on the coil, or we can vary the strength of the current that we are passing through the coil. Either way, we can vary the M.M.F that is going to be set up. So, M.M.F is given by N into I, where N is the number of turns of the coil, I is the current flowing through the coil, and the unit is therefore ampere turns. We know the unit of current is ampere and N is the number of turns. Therefore, it is very simple to remember the unit of M.M.F is ampere turns. M.M.F equals N into I, and it is expressed in ampere turns. So, it is the force which is required to create magnetic flux in a magnetic circuit. Next, we will move on to the definition of permeability. Permeability. Permeability means to allow. Just the English term, if you take permeable, it means to allow. So, here permeability of a material indicates the ability of that material to allow magnetic flux to exist in it for a certain magnetizing force. So, it allows, it is the ability of the material to allow magnetic flux to be set up in it or to exist in it. That is known as permeability of a material. Now, permeability is different for different materials. It is very much analogous to conductivity of a conductor. So, here is a simple circuit you can see, where this represents the EMF and this is a closed circuit having this the resistance of the wire. You can include a resistor here, and whenever a current passes through it, the resistance of the wire opposes the flow of current. So, similarly, you can here observe a magnetic circuit here, where this is the coil, a number of turns are present on the coil. The coil is being energized, and when the coil is energized, it sets up a magnetic flux. See, what you can see as the dotted lines here, what is shown here is nothing but the flux. So, the coil produces an M.M.F, because of which a flux is set up in the core, in the magnetic core. Now, there are two types of permeabilities for a magnetic material. Namely, one is absolute permeability, which is represented as mu A, and another is relative permeability, represented as mu R. So, for any magnetic material, there is going to be two permeabilities, namely absolute permeability mu A and relative permeability mu R. For measuring the relative permeability, vacuum or free space is chosen as the reference medium. So, relative, whenever we say relative means what? With respect to another parameter, with respect to something else we are going to express. So, here whenever we say relative permeability, it is usually permeability of any material that is taken with respect to vacuum or free space. So, this vacuum or free space is chosen as the reference medium. Absolute permeability of air is represented as mu naught and its value is 4 pi into 10 raised to minus 7 Henry per meter. And relative permeability of air represented as mu r is always equal to 1. Now, let us see the definition of absolute permeability, which is represented as mu a. Absolute permeability of a material indicates the ability of that material to allow magnetic flux to exist in it. So, it is very much similar. You know the classification of materials, like it can be classified into conductors, insulators and semiconductors. So, we tell that, how do we define conductors? We say that conductors are those materials which allow electric current to pass through them. Likewise, here when we say permeability of a material, of a magnetic material, it means by what is the ability of that material to allow the magnetic flux to exist in it. So, it is analogous to conductivity of a conductor. Conductivity of a conductor. Conduct means what? Allow to pass, allow to pass, that is conductivity of a conductor. So, for any magnetic material, it will have absolute permeability, which means or which indicates the ability of that material to allow magnetic flux to exist in it. Now, it is defined as the flux created per unit area of the magnetic material for every unit of magnetizing force applied to it. So, here pay attention here to the definition of absolute permeability. We just understood what is permeability, that is, it allows the magnetic flux to exist. Now, coming to the definition of that, it is defined as the flux created per unit area of the magnetic material. So, for every unit area of the magnetic material, for every unit of magnetizing force H that is applied to it, what is the flux created? So, this factor, this parameter varies from material to material. Okay. The SI unit for absolute permeability is Henrys per meter. It is expressed in Henrys per meter and it is given by the equation mu A is equal to B by H. So, whatever is the definition here has been translated into an equation here. You can observe that. What did we define it as? Flux created per unit area of the magnetic material. So, what is flux per unit area? We already studied that flux is represented as phi. Flux per unit area is nothing but flux density, which is represented as B. So, we have studied here flux density. You can observe here we have studied flux density B, which is nothing but flux per unit area. Flux per unit area, which is expressed in Weber per meter squared, where phi is the flux, A is the area of the magnetic field. So, here in the definition, what are we telling? It is defined as flux created per unit area of the magnetic field. So, flux per unit area is nothing but flux density represented as B. For every unit of magnetizing force applied to it. Now, how much flux is going to be set up depends upon the amount of magnetizing force that is being applied to it. Thereby, permeability indicates what? The ability of the material to allow magnetic flux to exist in it, So, if it has to exist in it, so what is the flux per unit area that it can set up depends upon the amount of magnetizing force that is being applied to it. So, that is why it is given by the equation mu A is equal to B by H expressed in Henries per meter. Next, we will move on to the definition of relative permeability represented as mu R. Relative permeability of a material indicates the permeability of that material as compared to the permeability of air. So, you have to understand, relative means we are comparing with something else. So, all of you are familiar with the word relation. When we talk about two people, we tell how are you related to him. For example, you say he is my uncle, she is my aunt. So, that is the relation that you are going to express one person with respect to the other. Likewise, here whenever we use the term relative, it indicates that the permeability of that material, that is whichever material we are considering, whichever magnetic material we are considering, as compared to the permeability of air. So, of the material with respect to air, that is known as relative permeability. Now, coming to the definition of relative permeability, it is defined as the ratio of flux density created in that material to the flux density created in air for the same magnetizing force. So, that is very important. So, how is it defined? It is defined as the ratio of flux density created in that material. That is, you are going to apply a magnetizing force. For example, suppose this is a material, let us assume that this is a magnetic material and I am a wire or coil of wire is wound around this, I am energizing it, passing current through it, then it sets up a magnetic field around itself or a magnetic flux around itself. Now, what is the flux density? Flux density is flux created per unit area. It is the flux created per unit area of the material, created unit area of that material. So, it is the ratio of flux density created in that material, whichever material you are going to consider, that material to the flux density created in air for the same magnetizing force. So, I am not going to change the magnetizing force, it is going to be the same in both the cases. Then when you take a ratio of that, it is given by mu r is equal to B material, that is flux density in the material by B air, means flux density in air. Now, this is just a number, because we know that what is the unit of flux density? It is Weber per meter square. Here again it is Weber per meter square. So, both of them, the numerator and the denominator, it gets cancelled. So, it is just a number. Okay. So, here you can see whenever we can divide, consider this equation mu r of B material by B air, divide both numerator and denominator by H. H is the magnetizing force, and important thing you have to remember is we are applying the same magnetizing force H. So, numerator B divided by H, then denominator also B naught represents the flux density of air. B naught represents flux density of air, and that is also divided by H. And we know that B by H is nothing but mu A. We have already defined, when we define the absolute permeability, it is given by the equation B by H, B by H, and mu naught is nothing but flux density with respect to absolute permeability with respect to air. So, B by H divided by B naught by H, when you simplify, you are going to get the equation mu r is equal to mu A by mu naught. Therefore, mu A, which is absolute permeability, is given by mu naught into mu r. It is given by mu naught into mu r. So, absolute permeability is the product of mu naught into mu r, where mu naught is the absolute permeability of air and mu r is the relative permeability. Relative permeability is nothing but it is the ratio of flux density of the material with respect to air. Next, we will move to the definition of reluctance. Now, what do we understand just by the simple word, English word reluctant? Reluctant means hesitant. Hesitant, you are hesitant, you do not want to allow. It implies a meaning like that. Okay. Now, applying the same thing here, reluctance of a magnetic material is the property of that material by virtue of which it opposes the creation of flux in it. So, what do we understand? Reluctance of a magnetic material is the property of the material by virtue of which it opposes the creation of flux in it. That is, you can understand that it is a property of a material. So, it varies from different magnetic materials. Some magnetic materials may easily allow flux to be set up in it. Some magnetic materials may be a little more hesitant to allow creation of flux in it. So, it is a measure here. Reluctance of a magnetic material is the property by virtue of which it opposes the creation of flux in it. It is very much similar to the resistance in case of an electrical circuit. And the unit of reluctance is ampere turns per Weber. It is given by this equation, R is equal to M.M.F by phi. F here stands for M.M.F. M.M.F means magnetomotive force. Magnetomotive force. Phi represents flux. Phi represents flux, and reluctance is given by the equation M.M.F by phi. We know that the unit of M.M.F is ampere turns. Just now we have studied M.M.F is equal to N into I, where N is the number of turns, I is the current through it. We saw it. So, here you can observe here in the magnetomotive force we just now studied, M.M.F is given by N into I, where N is the number of turns, I is the current, and it is expressed in ampere turns. So, here it is nothing but F here represents M.M.F divided by phi, which is flux is in Webers. M.M.F is in ampere turns, flux is in Webers. Therefore, unit of reluctance is ampere turns per Weber. So, it is nothing but opposition to the creation of flux, very much similar to resistance in case of an electrical circuit. What is resistance? Opposition to the flow of current. Here opposition to the flow of flux is known as reluctance, and its unit is ampere turns per Weber. Next, coming to the law of reluctance. Reluctance of a magnetic circuit is directly proportional to the length of the circuit, inversely proportional to the area of cross section, and depends on the nature of the magnetic material. So, suppose we consider this to be the magnetic material, then the reluctance of this magnetic material is directly proportional to the length of the circuit, inversely proportional to the area of cross section of the circuit, and depends upon the nature of this magnetic material, which is given by mu. We have already studied that, absolute permeability, relative permeability, etc. The equation governing this law of reluctance is therefore R proportional to L by A. R proportional to L by A. You can observe here R is the representation of reluctance. It is directly proportional to the length and inversely proportional to the area of cross section. So, R proportional to L by A. When we convert that proportionality symbol into equality symbol, we are going to write it as L by mu A, where mu is the permeability of the material, magnetic material. Therefore, L, that is equal to L by mu can also be represented as mu naught into mu R into A, because just now we studied what is mu A, mu naught into mu R. So, we are going to substitute this mu as mu naught into mu R into A, and the unit is ampere turns per Weber. So, here you can see that L proportional to R proportional to L by A. Therefore, R is equal to L by mu A, where mu is the permeability, and it is can also be written as mu naught into mu R. So, L by mu naught into mu R into A, and the unit is ampere turns per Weber. Coming to the relation between M.M.F, reluctance and flux. Flux created in a magnetic circuit is directly proportional to the M.M.F applied to the circuit and inversely proportional to the reluctance of the circuit. So, phi is equal to M.M.F by R, M.M.F by R. So, this is the relation between M.M.F, that is the magnetomotive force, R is the reluctance, and flux. So, magnetomotive force is responsible for setting up of the flux, and there will always be some opposition for the creation of this flux from the magnetic material, and that is the reluctance. So, combining or trying to strike a relation between them is given by this equation. Phi, that is the flux, is equal to M.M.F by R. M.M.F we know can be represented as Ni by R. Ni is where N is the number of turns of the coil, I is the current flowing through the coil, and the product of N into I gives the magnetomotive force. It is the force responsible for the creation of flux in a magnetic material. and R is reluctance, where R reluctance means it is the property of the material by virtue of which it opposes the creation of flux in it. So, one is trying to create a flux in it, the material tries to oppose the creation of flux in it. So, that is given by phi equals Ni by R, and the unit of flux is Weber. Now, this corresponds to the Ohm's law of an electrical circuit. So, it is very much similar to the Ohm's law of an electrical circuit. So, with this we come to the end of this chapter, where we have learnt about magnetic field, magnetic flux, magnetomotive force, reluctance and flux density.